screen here. Okay, so ladies and gentlemen, before we dive into modifying that model, I'm going to go and have a little bit of discussion about this sort of modeling. So discrete event modeling as the third major type, we actually saw this on the very first day. Some of you may remember this. We went to a model called Trauma Center. It's under the healthcare area of the simulation of the help system here under example models. And we saw a larger facility. Individuals were moving through the facility. They could arrive either via an ambulance or via or via on foot. They would register and they'd go and be matched up with services here. So some of them would go to these rooms to be inspected. Others would go to an area involving X-ray machines or a certain type of scanner, a VQ scanner, which is used for a certain type of understanding of heart-related health conditions, etc. So within this sort of model, we had individuals flowing through this facility. This sort of modeling is extremely common. It's very popular, and it's very widely used in understanding the effects of service delivery over time, and particularly bottlenecks within that service delivery, waiting times in that service delivery time and system, and our ability to process individuals. So within this context, a lot of the attention is on two things. Number one, there's a workflow, which is defined in a structured way. It's defined in a way that's not necessarily strictly linear. We can have branches, we can have loops, but it defines a series of stages associated with processing of individuals flowing through the system or of objects flowing through the system. Secondly, we're capturing within this workflow the effects of resource constraints or resource limitations. So in order to progress down through this series of processes, there's resources that are needed. So for example, here there's an indication that someone will undergo a CAT scan, a CT scan. This is a type of scan that provides extra insight, similar to what an X-ray gives, but in greater detail and in greater thoroughness. And this CT scan, in order to be to have that underway, we need to have access to the CT scanner. And if one person's in there, another person can't be in there. So there's resource limitations. There's one CT scanner, only one can be in it at the time, or there's 10 of them, and we can have a maximum of 10 people who occupy them. Now, within this context, we're going to have individuals, in this case, people. In other cases, they may be cars under assembly. It could be a piece of paperwork that have to be processed. And those flow through this pipeline, through this workflow. And they undergo particular processes at stages of the workflow. And if resources are not available to process a given person, let's say, who's waiting for a CAT scan, they'll simply queue up. They'll wait for that resource in most cases. So this sort of modeling focuses on resource availability, the occurrence of queues or waiting lists, processes that process individual and flowcharts that define those processes, and in some cases, physical movement within a facility. So within this sort of modeling, we're going to have these things called entities, which you could think of as, at a certain level, as being similar to agents, but these entities are typically more passive. Agents within our model might do things like infect each other, connect to each other, pass messages to each other, pass a rumor, and interact with each other in terms of affecting each other's behavior. Entities within discrete event modeling are more or less independent of one another, with one key exception. One can keep another one waiting, but they don't typically interact in a fulsome way with the environment or with each other than through these processes. So entities will flow through these processes. Flowcharts will specify that process. This is the workflow here, and it's defined as a sort of flowchart. Resources are required for processing them to go from one stage to the next, very commonly. And there's entity interaction with resources. Because I'm undergoing a CAT scan or an ultra scan or a VQ scan, because I'm under inspection by a doctor, I reserve that resource. So while I'm in the CAT scanner, I take up that CAT scan resource. I seize it is the term for it. I seize that resource, and then at a later point, I release it. Okay, so that resource is allocated to me for some period of time. And then at some point, I'm done with it, and I move on. If I'm being worked up by a doctor, if I'm undergoing a physical examination by a doctor, I've seized that doctor for that period of time. They work me up. They leave the room. They can go to another patient. I release them from for that reservation. They're no longer allocated to me, and they go on and deal with another patient. Okay, so we're going to have these workflows whereby entities can interact with resources by attaching to them, obviously by seizing them and releasing them, or by attaching and detaching, which will allow them to move together. In many models, we're going to have physical homes for resources in the sense of a physical location and movement paths within a facility. Okay? We're going to see how within this sort of modeling, we can define these workflows, and we can define the processes within the workflows that allow for movement within that context. The key resource or the key concept that we're going to be highlighting at first is this notion of an entity. And the entity is what flows through this workflow. In many ways, this is an entity processing type of model. Okay? Entities flow through, they're operated upon by processes, and eventually they often flow out. Okay? They'll be routed around through this process. So an entity might, for example, flow down here at the top. We find that a CAT scan is not needed. They come down here. We find that a VQ scan is needed. This entity is the thing doing the flowing, and it's being processed by each of these components of the workflow as it flows through. So these entities are predominantly passive. Things happen to them. They undergo VQ scanning. They undergo X-ray scanning. They undergo a workup by a doctor. They emerge into the system, and often they exit the system, and after that, they disappear. This is in contrast to an agent-based model where agents might persist for a very long period of time. Yeah, you bet. And they'll disappear from the system after they, within a discrete event simulation, they'll disappear after they leave, whereas in an agent-based simulation, we'll often have them sticking around for a long period of time. Typically, we have many entities flowing through a given system at a point in time, and by subclassing the entity class, by creating variants of it, we can keep track of added information. Okay. And often entities have a certain location in space as well. So we're going to be simulating a set of entities within our model, and we're then going to have resources that are needed to deal with them. These resources will be things like doctors and nurses who allow these entities to flow through the system over time. So within our model, we're going to set up a clinic which will allow people to flow through it, and we will then have resources that limit how they can be processed over time. Okay, and these resources will come in pools. We'll have a pool of doctors. We'll have a pool of nurses. You coming into the clinic will allow you to be operated upon by any doctor and any nurse. It's kind of like you go to the walk-in clinic over on 8th Street. There's, at any one time, a set of doctors there. You'll be assigned to one. That doctor will see you. Some nurse or nurse's aide will come in and see you. And you go there another time, it'll be a different doctor. And that's the sort of situation that we're going to be capturing within today's model. Okay, so having talked about that, I'd like now to move back to AnyLogic. And I'd like to open up the model that we built last time, and let's just try to remember what we did last time and how we built it out of pieces, because we're going to be modifying some of those pieces. So within this model, we have a model with a GIS environment. Within this GIS environment, we have a set of agent populations which are defined. Those populations are defined over here on the left-hand side. So we have homes, workplaces, the population as a whole, and then a little bit over here we have clinics. Our focus today is going to be on the interaction of populations in clinics here, okay? The clinics are going to serve as the basis for service delivery. Individuals coming into the clinics will be operated upon by resources such as doctors and nurses, etc., and will then be conferred some change in their health status as a result. Okay, so our focus here is going to be on this clinic. But as a reminder, within this model, if we ran it as it stands now, individuals within the population are going to be circulating. A given person can be at a given time in one of a set of states. When they become infected, their normal routine of going back and forth to work and home will be broken, and they'll sometimes seek care, and they will seek care in a way that brings them in to a clinic. Okay, we're going to go to the nearest agent amongst the clinics for that person, right? So here we have these individuals. They are going back and forth between home and clinic. Some of them are ill. So here they're going home, for example, at the end of the day. Some of the individuals that are ill will, over time, decide that they require care, and they'll present for care at a clinic. So over time, some of these individuals will come into the clinic to seek care, and at which point, currently, they will be cured by result of being in that clinic for 3 hours. So that's what we've shown right now. They actually go to the clinic right here. So they move to the nearest clinic. But having gone to that clinic within 3 hours' time, they will simply move to home, and we're going to tell them that they're cured. Okay? We are going to change that by actually having them interact with a clinic. And this model will take us again into the sphere of hybrid modeling. We saw that before with system dynamics and discrete and agent-based modeling. And today we are going to try it instead with discrete event and agent-based modeling. Okay, so that's where we're going. And I'd like you to now go and come up to the clinic area. And I'd like you to open up clinic so that we can see the elements here. We are going to go open up within the clinic a representation of clinic that is going to capture people's flow in the clinic. So I'd like you to go over to the palette here with the clinic open. I'd like you to go over to the palette, and I'd like you to go to an area of the palette which we haven't previously used, but it's the process modeling library. It's actually the first one that's shown there, so it's possible it's already open. And you'll notice that this library gives us a set of operators here to work with. We're going to be working today with a subset of these, and there's additional power available for describing additional types of services that we won't be touching on today. But fundamentally, we're going to compose together a workflow of the sort that I've been talking about, namely this sort of workflow like this, okay? So let's go to AnyLogic, and we are going to go here and drag into this, the clinic, a description of the clinic's operation, okay? So I'd like you to drag in here a first element, which is called an entry or enter area, okay? This is going to be the entry point. So this is going to be called walk-in. Okay, it's going to be the area where people come into the clinic. Okay, next, I'd like you to go and set up a queue, which is going to be actually, first we're going to put a delay in here. So there's going to be a delay that's going to be up here, the third one down. I'd like you to drag it in. You notice if we drag it close enough to this guy, it's going to place it in a connected way. And this is going to be called workup. Okay? Workup. Okay. And I'd like you to go and finally add an exit here. Okay? An exit component where they, return home. Okay? So individuals are going to flow in, they're going to be worked up, and they're going to go home. Now, we can, associated with this workup, we can put in place an indication of how long people are waiting. You'll recall that the model as a whole has a time frame associated with it in hours, but you'll notice that right now the delay time is measured in seconds. So we want to change this. I'd like you to go here and change this. You can leave this, which is a draw from a triangular distribution. It's a draw from a distribution whose probability distribution function, or PDF, is, it looks like a triangle here. So it extends from, and that's not quite a great indication of it, extends from 0.5 hours, 0.5 hours here, to 1.5, and its mean and its mode, the single most common value, the mode, and the mean is 1 hour. Thanks. You serious? Linux. Okay. So it wasn't my Linux, it was that's Linux. Yeah. Okay, so this is going to be hours here. Okay. Glad to contribute to the department. Okay, thanks. Yeah, so Greg will hear your work. Okay, thanks a lot. So this is going to be between 0.5 and 1.5 hours, with the single most likely value being 1. Okay. Now, here we're going to set this to have some maximum capacity at first. Okay. We're just going to pretend any number of people can be handled at once. No matter how many people come in, they can undergo this workup at a single time, at the same time. So we have a huge room full of doctors ready to serve. People come in. Each of them is given out to one of the doctors. There can be 20 people, 30 people, 50 people there at once, and they'll all be handled. This is the idea. With what this currently represents. Okay, so I'd like to go and next connect this to the actual flow of people within the clinic. So I'd like to do the following. I'd like you to go back to the person and find the place where they go to the clinic here. Okay, here they move to the clinic, and they are now going to be waiting in line at the clinic. We're going to need to change this just a bit to remember which clinic this is so that we can ask themselves to move to it, but also to get in line there. So this is what we're going to do. We're going to take this code. Hopefully it should be bigger than last time. We're going to create a variable called nearest clinic. Actually, it's of type It's a reference to type clinic, and it looks like this. So this is how we get it. This is what it's initialized to. It's initialized to a reference to the nearest clinic. Okay? And they're going to move to that clinic. But more than that, they are going to be placed in line at that clinic. Okay? So how we're going to do this, we're going to say this, or sorry, we're going to say, excuse me, nearest clinic dot walk in, that was that block, dot take, and we're going to say take me into the clinic. Okay? What this is going to do is it's going to place this agent who is seeking care within the clinic. In other words, they're going to flow in as an entity here. Okay? They flow in as an entity into that clinic. And by so flowing in, they'll be part of this process. They'll be worked up in between half an hour and 1.5 hours, and they'll leave. Okay. Take this. Yes, and I'll explain that again. So we're saying, okay, so this is getting a reference to nearest clinic, and obviously we're moving to it. Then we're saying for that clinic, this walk-in area, which is this guy here, take into that walk-in area myself. This here is occurring in person. We're in person here. This is code in person. So this is referring to the current person. Does that make sense? So it's enrolling the current person within this clinic workflow. Okay? Okay. And ladies and gentlemen, we are going to now eliminate this. We're going to change this return flow from being a timeout to being a message flow. Okay? It's going to be triggered by a message, I should say, a message transition. So instead of just coming to the clinic and 3 hours later they're going to go home cured, we're going to instead have this be triggered by a message. And that message is going to be a particular message, okay? And for now, it is going to be messages.cured. Okay? So when they're cured, they're going to go home, okay? So the message here is messages.cured. What did I do here? I just changed this a little bit in two places. The first thing is, instead of just going to the nearest clinic, I actually go to that clinic and I enroll in it. I enter into the workflow of that clinic. In other words, I enter into here. Secondly, to leave, I don't just leave in a fixed 3 hour time period. Instead, I leave whenever I am cured. Does that make sense? Now, what's missing here? If this is the logic, if they're going home here once they receive this message, what still has to happen? What part of the dynamics haven't we changed yet? Yeah, so here they're receiving the message. So now we got to send that message. So let's go over here, return home. And actually, let's say for now at return home, when they go to this point, we are going to send the message. I'm going to say this dot send. Okay. I'm going to send it to which object? I'm going to send it to the current object. Okay. And if you look at this thing here, it'll tell you there's a thing called agent, and that's what we want to send it to. That's the entity we're dealing with. And what's the message we want to send? It's messages.cured. So when this agent reaches this point in the process, we're going to send that entity a message saying messages.cured. Okay. So now we've taken the control over how long they're in this clinic out of the person. Before, this used to be, you'll recall, just 3 hours. Now we've changed it to be a message-based transition. So someone else triggers when we're done, when we're going home. Who is that entity that, or who's that actor that triggers it? It's this clinic. It's at this clinic that it sends a cured message to the underlying agent that triggers them to go back home. Okay? So that's what we're doing. Right now, it's extremely simple because we haven't put in much workflow logic, but fundamentally, we've undergone an important transition. We've taken the determination for how long it takes them to go home away from the agent and put it in the clinic. And then we're going to evolve the clinic to be more and more sophisticated. So we've taken that first key step to put the responsibility for the clinic to cure them and for when they go home rather than leaving it with the person. Okay, so this is the responsibility of the clinic, and we'll be able to examine the effects of crowding, etc. Okay, so right now, no matter how many people come in here, that's why its maximum capacity is checked, they leave within somewhere between 0.5 and 1.5 hours. Okay, so let's go run this thing. Okay. Okay. Send. Oh, you know what? I reversed it. Sorry, folks. When I was a young man, we had to remember that all in our head, and now we don't, and I forget more easily. Okay. So send.messages.cured, agent. The agent has to go next. This is the person to whom it's sent. You can see that through the autocomplete here. If you were to go look, we're sending it to a certain message. This is the message to a certain agent. Great. Let's go run this model. And what we will see is something quite similar to before, except people are going to be cured by the clinic even more quickly. Okay. Occasionally, if you come into the city hospital, you'll notice city hospital right now has treated one person. That's what this one means. One person has flowed through to this point. One has flowed through to that point. If we were to go look at RUH here, so that's City Hospital. Let's go here. Look at Royal University Hospital. They've treated 5 people so far. Okay, and if we were to run it flat out, it looks like it's controlling the spread of infection. It looks like everyone's recovered here now. Okay, great. Let's go look and ask, suppose this workup took a longer time. Suppose it weren't 0.5 to 1.5 hours, but days. What do you think would happen now? Anyone? Suppose it offered really slow time to treat someone. What do you think could happen then? How might it be different? Well, let's go see. Go to Royal University Hospital. Now it's treated 26 people, okay, over the course of the time. Anyone want to conjecture why that is? Why did it have to treat so many more? How if it took 0.5 to 1.5 years? What do you think we'll see? Surely someone must have a conjecture about that. If it takes years to be treated, what do you think is going to happen? Sorry? You'll die, that's right. Yeah. Okay, well spoken. Certainly it's going to be a lot more serious situation. And this is going to get us to an important point, which is at some point it's unrealistic to expect people to be able to wait, right? Here the count is still going up. In short, not only are people dying, or not only are people waiting so long they could die, it's actually the infection continued to spread for a much longer period, okay? So ladies and gentlemen, 2 points here. The amount of time it takes to treat someone is going to be very importantly related to what goes on in the population. If we're not treating people fast enough, the infection may spread more. And that's exactly what we saw as we upped the time units associated with this from hours to days to years. We saw more people getting infected yet because we're not treating those who are infected and they're spreading it in the meantime. Okay, so there's a link here between what's going on in the clinic and what's going on in the broader population. Okay, so we're going to expand on this and put in place some additional mechanisms. Now, in order to do this, I'd like to put in place just a couple of mechanisms, okay? I'd like to put in place, first of all, a little bit more space between walk-in and return home. And I'd like to copy in here from the palette, I'd like to copy in something called time measure start and time measure end, okay? Oops, meant to do time measure start first. And if you sort of create it here, I think if you bring it down here, it'll actually, okay, yeah, it won't properly wire it up, but there should be a way that it's all wired up. Here we go. Okay, we have two wires. And this time measure start will measure how much time things are going to take from that point. And then time measure end is going to measure it for the end here. In other words, it's going to measure the time from the start to the end. So the time measure end, we dragged it in there, and we're going to specify the block from which it starts measuring time, and that's this one here, okay? And we'll keep up to 10,000 data points, okay? So this just, the job of this in life is to measure the amount of time it takes to go from time measure start, that's the thing specified here, to time measure end, okay? So what do you think that time's going to be on average now with this very simple setup? What do you think it's going to be? Yeah, it's going to be an average of about 1. Why? Because, well, some of 0.5, but some of 1.5. And the mean of it, as shown on the board there, as well as the mode, is 1. Okay? And the fact the mean is 1 is going to mean it, on average, it's going to be about 1 hour. Okay? So if we were to go look here at City Hospital, or if we were to go look, better yet, at Royal University Hospital, which is serving somewhat more patients, we should see, subject to sampling error, an average of about 1. Okay, and here the mean is 0.993. Yeah. Yeah. Good question. So I dragged from the palette. So the question is, how do you set up time measure end? So having set up time measure start here, make sure it's hitched up to both these guys. I then drag time measure end over to this one. And time measure end, when you set it up, first of all, you want to make sure it's configured properly like that. But you have to set the time measure blocks here, the time measure start blocks. And I did a plus and picked it. And that basically tells it to, hey, to measure the time from this to this certain point, okay? So this is the end point of the measurement, this end, and this one shown here is the start point, okay? And you'll notice that when we did this, we got something very close to the theory. If we were to say that this takes, 1 to 1.5 days, something like that, we would get more people queued up and we'd get more statistical reliability. But in both cases, it will be about a corresponding amount of time as indicated by the theoretical distribution is likely. So here we go with 26. We have a mean of about 22.7 hours, just about a day. And then there's a minimum, a minimum that's been experienced and a maximum among these 26 people that have flowed through. And there's an indication of how many people took different lengths of time down here. Okay, so this provides us with a way of measuring the time from the start to the last, okay? So, ladies and gentlemen, now, this is what I want to do. Right now, we've been assuming made a very generous assumption, even a heroic assumption. We've assumed that people can get worked up. However many come in, they can be worked up within, let's change that back from days to hours, this amount of time. And in fact, we know that's not so. If any of you have gone to the emergency department recently, you will find that sometimes you have to wait longer if your condition is less serious, particularly. So, or is perceived as less serious by the triage nurse. So here, the workup, we're making a very generous assumption, assuming that everyone can be treated at the same time. What's more likely to occur? If you go in to the emergency department, ladies and gentlemen, and all the beds are taken, which will not infrequently happen when you walk in. If you're not a very serious case, they won't be able to take you immediately. What do you think happens? How do we respond to that? Now, you could send to a different clinic, but there's also an area there where you what? Where you wait. And so we're going to represent that waiting explicitly, okay? We're going to change workup to no longer be maximum capacity. We'll assume that there's only one person who can work you up, say one nurse there. And we will add in from the palette. Oh, okay, I just dropped something. Okay. We'll add in from the palette something that's going to represent a queue. Okay. This queue is going to provide an explicit representation of those who wait. Okay. So this queue is going to be waiting for care, okay? And you're just staying there until you get worked up right now, okay? And we will assume that this is at the maximum capacity, okay? In other words, only one person can be treated at the same time. So there's only one person who can get treated. The rest will wait as long as, and there can be as many of them waiting as needed to let them eventually proceed. That's why we said maximum capacity here. Okay, so here we have a service. People are flowing in through this. Before, they were just being worked up and left. However many came, they could be worked up. Now they will wait here until this workup is free, and they can be worked up. That's the theory here. That's the theory. Okay. Now we're going to see what happens here. Okay. So here we have a situation where we are going to have this flow, and what we'll find is that here we've treated 5 people in RUH, and you'll notice that the average length when they came through was 0. We actually had enough people, few enough people coming through. They weren't waiting for long. Let's change the situation now a little bit. Let's actually change it so that we have a more serious, within this spread, we have a more serious sort of spread of infection, okay? So what I'm going to suggest here is that we put in place a mechanism so that we have an outbreak that does take longer or persists at a more serious level. Okay, so I'd like you to go over to the simulation here, and we're going to put into place a contact rate. Instead of being 1.0 per day, it's going to be 10 per day. Okay, so 10 contacts an individual has per day with somebody. Okay, and now we have a much more serious situation. We have individuals who are presenting for care over time, and the number of people here is rising over time. At City Hospital, we've dealt with about 50. Let's go to RUH. Okay, so we're going down to Royal University Hospital, and here we've dealt with about 10 times as many. Okay, Oh, excuse me. This is about 300 now. Let's go click on this waiting queue. And you can see that we're still treating them in a fast enough way that it's a very small average waiting time or number in the queue at any one time. Okay, very, very small number in the queue. If you change the workup time for hours to days, what we would see is a much more serious queue yet. We'd see a queue which is much longer because people have to wait for longer because others are in front of them in the queue. And I'm going to simulate that here. And here people are coming in for a much longer time. And for example, here's the queue length. It's somewhere over 10. So what did I do? Ladies and gentlemen, I went and I changed the simulation to be 10 contacts per day. I further changed this workup to wait on the order of days. And you'll notice that there are a lot more people in the queue. People are waiting for longer time to get treated. Okay. And while they're in the queue, they're potentially spreading infection. Okay. So that shows some interplay between the two. I'm going to change it back to hours and simply up the amount of time taken. We're going to up this for between 4.0 hours and 8 hours with an average of 6 hours. And we'll seek something that's a little bit longer, but it's not something that keeps them overnight or for days. Okay, so once again here we're having a situation where people are waiting to some degree, and for a larger hospital like RUH, it is particularly serious. Okay, here we go. And so we have some people waiting in queue. Okay, so next, ladies and gentlemen. We've just been modifying this so we get a more regular flow of people through here, and so we can look for the impact on queue size. The next thing I'm going to do is I'm going to model the potential for people to leave the system. Okay, in other words, some people may leave without being seen because they're waiting too long. Okay, and if they leave without being seen, they won't be cured, but they will no longer be holding back the queue, and others may get served instead. Okay, so we're going to have to change things around a little bit. What's one way I have to change it to have them leave without being seen? I told you they won't be cured, so what are we going to have to change here? Sorry? Yeah, so the message send can no longer be done here if the people leaving are also leaving from this same place. This right now is curing everyone. Really, we want to cure them only at the end of the workup. Okay, so we're going to take from return home, we're going to take this out, and we're going to put it in workup here. Okay, and when they finish workup, at the exit of workup, we're going to send a message that says they're cured. Okay, next, we are going to connect something from this guy over to return home. And you'll notice that at the top of this, there's two special components here. One of them is for preemption. One is for timeout, okay? And I believe it's the upper right one that we want here. I may double check this in just a second, but I'd like you to double click on it. And you could start extending. I'm going to double click here. Okay, it's not going to incorporate, so fine. I'm going to drag this over, okay? And I am going to place this up here and this up here. And basically, this is going to be providing a separate way for people to leave. Now, this is going to cause a little bit of an issue with time measure end, but I'm going to try to change that by having another time measure end here. So let's first focus on this guy here. So waiting for care, we're going to go down to the advanced area, and we're going to do enable exit on timeout. In the timeout that they're willing to tolerate, we'll let them wait for up to 2.0 hours, okay? Not seconds, but hours. So they're willing to wait in line for up to 2 hours here, is what we posit. We could obviously draw that from a distribution. A given person, some may be willing to wait longer, some less. And basically, if they don't get that time, they'll leave via this other path. But as I noted, we need to put in place a time measure end. How do we do that? Well, we went here, I scrolled down within this queue, and I clicked enable exit on timeout. And I said it's a timeout of 2 hours. And what that means is that that if they're not served in that time, they'll balk. They'll leave. They won't wait, and they'll depart the queue. But they won't be cured, because now we put cure into the place here in the workup. Okay. Finally, we need to go put in up here. We need to put in a time measure end. Okay. Time measure end up here. And this is going to be time measure end for bulking. And we have to add, it's based on time measure start. Okay. So we're going to put this one down here. And I'll actually name this one differently. Non-bulking. Okay. Here we go. Time measure and non-bulking. Okay. So now we have this time measure end, and it's measuring something from the starting for those who leave. Otherwise, time measure end non-bulking is for others who who are in fact cured. So what's the impact going to be of people leaving without being seen? What's the impact of that going to be? One thing is it's going to decrease the queue length, but what's another thing that's going to happen? They'll remain infected. They'll remain infected, yeah. And actually, just to sort of emphasize that a little bit more, in this block, the queue, I think I'm going to change the timeout to be 1.0 hours, okay, instead of 2. It'll make it more clear. So if they wait more than an hour, they're going to leave. They're going to leave still infected, and that means they can still spread it, okay? They will have occupied that queue in the meantime, blocked others potentially from getting service, and yet they're leaving without being seen. So if we go to City Hospital, for example, we'll see that 2 of them up here, you can see 2 have balked, and those people who balked here, they had done so after a shorter time than people waited here in for their treatment that actually led to a cure. For those who have been cured, the mean time to transition is 6 hours to this point, whereas for those who have balked, it's a mean of about an hour. I'm going to go down to the case of Royal University Hospital, which seems to get bigger traffic here. So here we go, Royal University. Boom. Here we're getting 29 people who balked. So about 30%, no, a little bit less than 30%, like 25% of those overall. And here, yeah, everyone who went this way, of course, it's 1 hour. They waited an hour and then they left. And for these others, it's close to 6 hours that they've been waiting. Okay. Now we have a situation where eventually got through the infection, but in the meantime, there were some people who balked, some people who therefore stayed sick. Yeah. To hear. Good call. Good call. Thank you. Thank you. So yeah, that's a loose end. Excellent point. I was mean to come to that, but I neglected to include it thus far. So return home, ladies and gentlemen. You'll recall that to go home, they need to be sent a message. So what we're going to do is we're going to need to separate out a cure from a go home message. Because now some people are going home without being cured. Some people are going home with being cured. So we need to go over to our palette, and we're going to need, excuse me, to the project area. We're going to need to go to messages here, and we're going to need to add in to the possible messages something here that's called discharged. So that's someone who's discharged. They're actually, we shouldn't call it discharge. It's more like a left clinic, because they might not have been formally discharged. Left clinic. They just said, I'm out of here. Left clinic, or departed clinic. That sounds a little bit better. Departed clinic. Okay. Departed clinic. So now, at this point, we're going to send a message, much as we had earlier. We sent a message for cured. We're going to do the same thing here, except instead of sending a cured message, we'll instead send a departed clinic message. Okay. And to return home. How did I do that? I went to option list, to messages, went to this thing, added one called departed clinic using this button. I then went here and said, send the agent a departed clinic message, whoever the agent is. Maybe they balked. They still depart the clinic. We need them to go home. Suppose they've been cured. They've still departed the clinic. We need them to go home. And finally, what do we need to do to finish the thought? Yeah, change the mobility state chart to have this trigger transition. Ladies and gentlemen, in software engineering in general, and modeling is no exception, work occurs in chunks often. If you have a thought, you have an intention to capture a feature, some functionality within code. Typically, that involves modifying things at several places, maybe where it's sent and where it's received. Maybe several different subcomponents to capture the logic of a new bit of functionality. It needs to go in the back end and the front end, and the business logic, for example. Here, it needs to go where the message was sent and where the message was received. This is a common pattern. There's chunks of work, logical chunks of work that are needed to complete the thought, to have a complete capturing of that intention. Within software engineering, we typically give that chunk of work to a particular software engineer, and the system is tested when that thought is complete. It is checked into the repo, to the repository, the Git repository or what have you, when that thought is complete. You don't check it in halfway through when it's only half done, because it's not functional. You do it once it's done, tested, and you check it into the repo. And this is an example of that. We really need to complete the thought. And in fact, earlier on, as Eric pointed out, we hadn't really completed the thought. Okay? So here, this message is triggered by departed clinic, which is sent by this thing here. And that was logically implied. The fact that we had to do that was implied, as Eric noted, by virtue of the fact that we moved the cured message over to workup. Had we left the cured message in here, it could have served as the indicator for departing the clinic. Okay, so let's run it. Ladies and gentlemen, now we have individuals who are going to the clinic and then returning home. You'll notice that this is hitting the servers here, presumably capturing sort of the transitions to the workplace and so on. But when people go to the clinic now, they will present for care in the clinic, and then they will be sent home at the end, regardless of whether they have balked, they've left without being seen, or whether in fact they were seen and are now cured. Okay, so people are going to the clinic. You could see them here. They're presenting for care at the clinic, and then they are heading home once again. And that's by virtue of that message. Okay, but we're not done yet. That was just adding some balking. Now we're going to do something more. I hope this is bringing out certain basic facts, though. I want you to understand. Part of the whole experience of doing this is to understand this point. People are flowing down through this. Some of them go one way, some of them go the other way. They're operated upon by the queue. They wait in the queue. They go through the workup. We're interested in how long they spend, how long the queue is, etc. But let's take it further. What we don't have here is something explicit to capture one of the key central concepts that we use for the motivations for why we use discrete event modeling. What is not represented explicitly but is central to discrete event modeling based on what I said? What's missing here? Begins with an R, ends with an S. Resources, ladies and gentlemen. We only have an implicit resource in that we say there's only one of these available for the workup at a time. In general, we have more complex needs than that, ladies and gentlemen. So what I'm going to do is I'm going to add in what's called a resource pool. We're going to capture resources of certain sorts, okay? And these resources are going to be initially of one sort. If time allows, we'll expand that, okay? We could have procedure rooms, we could have nurses, we could have doctors, etc. Okay, so what we're going to do is give ourselves a little bit more space, okay? And we are going to add into this model from the palette, we're going to add in a resource pool, okay? This resource pool is going to be a particular, it's going to capture a particular type of resource, which is going to be nurses, okay? Here we go. And so it's going to be called nurses here, okay? In the resource pool. Whoa, okay. Nurses. Okay. I don't know what quite happened there, but okay, next. We are going to go and we are going to further add in what's called a resource unit. And this is going to be called a nurse, okay? And you'll notice that it's actually going to add in an agent type there. So it turns out that in any logic, these are captured as agents. And so we're going to set the nurses here to be a resource unit of type nurse, okay? So the new resource unit will be nurse. So this is going to be a resource pool of nurses, okay? And initially it's going to be of capacity 1. We're only going to have one of them at a time, okay? And we're going to put into place here a little bit of logic governing the assignment of these resources to patients flowing through here, to the entities, okay? So specifically, you may recall in my earlier comments, I had noted in those slides that we have this notion of seizure. Seizure here means that we acquire a resource, we're allocated a resource, we're assigned a resource. We use different names for it, but the resource is something that's associated with a given patient for a certain period of time exclusively. At a later point, they release it, okay? So what we want to do here in the process modeling library is we want to drag down and we want to add what's called a seize block, okay? A seize block. Now, the seizing block, so it's going to be called allocate nurse, okay? And this is going to depend on a resource set. The resource set is going to be nurses, okay? And you'll notice that it provides, like this queue did before it, it provides a queue built in. It has a queue capacity. We really don't need to maintain both, so we're going to just wire this guy up to here instead, and we're going to remove this one here and have it instead just go directly to this. So it's going to seize the resource, it's going to wait, and it's going to have a maximum queue capacity, and it is going to have a exit on timeout associated with 1.0 hours, okay, just like the earlier one did, 1.0 hours. So, ladies and gentlemen, people are going to come here. They're waiting for a nurse to be assigned to them. If the nurse hasn't been assigned, they will, after an hour, they will balk. Otherwise, they will be assigned a nurse. They'll be worked up by that nurse. So the nurse will do an examination, confer a cure is the idea, and then they will leave. It would have to be a nurse practitioner to confer a cure, but we'll abstract over that. Okay, next. One thing that also needs to occur is we need to do what? We need to release the nurse. So we're going to need to add a block here, which is called release nurse, okay? She's or he is deallocated and can go treat other patients. Okay, so this is going to be release a nurse, and by default, it releases all seized resources. Okay, so now we're waiting for nurse. We could we could have more than one nurses, and as we'll see, we can define this much more flexibly than just saying there's only one thing to work up. So first of all, let's build this. Anyone want me to show part of this again? Yeah, allocate nurse here. I did resource set nurses. I did maximum queue capacity. And I said enable exit on timeout after 1 hour. That's what I frobbed there. Okay. Any other questions? Anyone want me to show something? Release nurse I just dragged in, and it already released all seized resources. So I just kept it like that. Okay. Okay, ladies and gentlemen. No questions? Okay, so let's run. Okay. So we're running this here. We have some infected people. I'll run it at full speed. And you'll notice now, if we go to the resources, we have a representation of the resources. Now, you'll notice here, for the resources associated with City Hospital, there's a number just to the left of it. Do you see that? Let's go down to RUH instead. If we go to Royal University Hospital, we will see a different number. What do you think that number represents? Yeah, how much they're being used. the fraction of time this nurse is actually treating a patient, okay? What fraction of the time they're actually seized? What time of the fraction of the time they're actually allocated to a patient, okay? So that's good. Let's now do something a little bit more flexible. We're going to modify the nurses to have 2 nurses, okay? But we will do so in a way that will take into account the need for breaks here. So there's a breaks schedule here. And we can actually specify here a schedule for that, okay? You'll notice that for this schedule, we'd actually have to specify sort of what is the schedule associated with this. And we could go see here, there's a resource task. Oops, it's not that one. Sorry, schedule. Here it is. Schedule for the nurses. Okay. And we can specify, for example, on certain days, at certain times, we have this certain schedule. And this could be sort of how many nurses are on at certain times, or it could be whether a given nurse is on or off at a certain time, etc. Okay, so we could indicate in short that at certain times there's more nurses, at certain times there's fewer nurses, and look for those indications for the size of the pool. For right now, we'll say it's an integer. By default, it's 1 here, and then we could define a particular sort of schedule here where we have for certain times between, let's say, 8 a.m. here, 8 a.m. and 5 p.m. here. So, okay, so let's say 5, and we'll just go to this, p.m. Then we will have 2. Otherwise, we have the default value of 1. Okay? So we'll have 2 nurses on at certain times during the day. Otherwise, we'll have just 1 nurse on. Okay? This schedule then could be used to define the schedule associated with the nurses. And you'll notice it says capacity defined by schedule associated with the nurse, and we'll pick the schedule here. Maybe I'll call it nurses staffing schedule. Okay, and whoa, wow, that's pretty. And then the nurses will be defined by and it's looking for that by the schedule here. Okay, so come on, home location, I'll say schedule, and I'll pick it out, the staffing schedule. So now we can have variable staffing at different times of the day. Sometimes there's 1 nurse, sometimes there's 2, and we could examine the impact of that sort of, okay, schedule is not defined for, okay, what did that say? Oh, the breaks, thank you. I didn't complete the thought with that. Yeah, so for the breaks, we actually are not going to, we're actually not going to have time to use that. Time is running out. So I will unselect breaks here. I'll simply say for the schedule, we'll do that. Okay. So now we have their capacity being defined by the schedule, and at certain times, City Hospital, for example, would have 1 nurse, and you'll notice it says sort of next in here, it changes to 2 nurses according to the time of day. You notice this is the time of day. It's mid-afternoon. It's approaching. It's going to shift over to 1. So here we have this changing schedule. Now, ladies and gentlemen, discrete event modeling is a rich area, and it's one I'm going to ask you to explore some and some take-home work. There's a lot where we've highlighted basic features here, and there's a lot further we can take them. But I want to draw attention to just a couple features. This will reiterate what I said earlier. Discrete event modeling is a type of modeling methodology that focuses on the flow of entities, in this case patients, through a defined workflow, which we've defined here, where those entities are operated upon by processes. So operated upon by processes. More or less passively, they flow through the system and are operated upon, say, by the workup or by bulking or what have you. And their progress along that workflow through these processes is governed by availability or not of resources. If the resources are not available, typically the response is one of two things. Either they wait or they bulk, or someone else preempts them. In other words, they come in and sort of override them. We've examined two of those, bulking and waiting. This sort of modeling permits us a way of very flexibly asking about how the level of resource availability, and in fact, although we haven't seen it this time, the location of resources affects the flow of these entities through the system. And often we're really interested in how long do things spend in the system, hence this time measure start, time measure end. How many entities can we process per hour, throughput? And we're interested in the length of the waiting lists, or the size of those waiting lists, or how long people spend in those waiting lists. We've seen hints of most of those items here. And it should be noted that we could capture this functionality within an agent-based model. It wouldn't be impossible at all. We could have nurses represented explicitly as agents. We could have patients represented as agents. We could have state charts that captured where they are in this process. We could have messages exchanged between them. We could implement our own resource allocation for nurses. There's no question we can do all that, but that isn't really the point. The point is this language is highly selected, highly expressive for characterizing these sort of problems, and allows us with just a very small bit of mechanism to characterize, for example, changing resource availability, which ripples through to changing flow within the system in a way that's quite visually transparent. You can parse it pretty well, and in a way that allows us to capture fairly complex allocation schemes with a fair degree of ease. This is only a very simple model. We could add in doctors and require doctors for certain procedures, nurses for others. We could add in procedure rooms, fixed assets like pieces of machinery or rooms that you need to go to them, or portable equipment, or mobile agents, individuals who can confer care, for example, like doctors and nurses, and who are mobile resources. So resources come in three types: mobile, like nurses; fixed, like rooms or pieces of heavy equipment; and resources that can be moved around but don't have agency themselves. They're not active resources. They can be brought, like a piece of equipment that can be rolled into a room and is not truly fixed. So this sort of modeling provides us this very nice language for characterizing flow of entities through resource-constrained processes, where those entities are predominantly passive. What we don't have here is individuals explicitly interacting except by making each other wait. The fact that I'm being seen by the nurse means you can't be seen by the nurse. And that's about the limit in this component of the model, this component here, of how the agents interact. They interact by keeping each other waiting, by starving each other of resources, etc. This is at an individual level like agent-based modeling, but it's a different perspective on it. Agent-based modeling, agent interaction with the environment is key. Here, agent characteristics are maybe present, but agents are more passive. Okay, so that's a bit of a glimpse of discrete event modeling in this context. We may continue on for a little bit more on this, looking at the issues of physical location within a facility and its interaction with travel times. But we'll also use this model as an example of a broader hybrid modeling scheme where we weave together multiple types of modeling. Because here we've woven together agent-based and discrete event simulation in a single model. So that's all for today. I'll be posting this model if anyone had trouble following along aspects of it. Thanks very much.